name is Cecilia, and I'm gonna present about Gwyneth, which is a research effort from Taiko that trying to explore the space of base interoperability and generalization. So I'm gonna give like an overview of synchronous composability and what does that actually mean. So in this area, like we're trying to like explore how we can communicate cross-chain. There is a EIP ERC 7683 or RIP 7755, which is an intent-based request protocol. Let's say Alice, who's living on the base chain, wants to do something on optimism. She will send an intent through it in the network, and there's some feelers that are incentivized to fulfill her intent. This is a one-shot message that like the user will specify her one-shot intents and hope for the best, right? And the feelers will be incentivized to do it. In this case, it's apparently, well, trivially atomic because either her intent gets filled or it's just completely discarded. However, it's definitely not synchronous, right? Because you don't have you can't have any guarantee at which whether anything will do with your intent. So this is a typical non-example of synchronous composability. Another non-example is if user sends HTTP requests to RPC calls for both chain. And if you look at the JavaScript segment from above, that is what you typically do in your wallet, right? You swap something on OP by sending an RPC request, you get some USDC out, and then you buy a meme coin on Taiko. And then you send another RPC to OP, the OP network, to sell the Bitcoin, right? So you're manually doing it through JavaScript, and that's apparently not synchronous because like network communication is intrinsically asynchronous, and it's also anatomic because during any of the steps your operation might fail, right? You can buy the NFT and the Taiko network goes down, so like you can't keep on your operation because you're doing it with your labor work. So that's another non-example. An actual example is this code right here. Like user calls this contract on Taiko, which directly modifies state on optimism, as if you are actually executing for both chain. So yeah, in this synchronous swap over here, like in the smart contract codes, you have like things executed on optimism, and then you buy meme coin on Taiko, like the middle line you're executing in the Taiko context, and then you switch back to optimism to sell your meme coin. In this case, it's perfectly atomic and also synchronous. Okay, so I just went over the what is synchronicity from an execution standpoint of the nodes, and let me go over an overview of what's going on in the space for like cross-chain communication. So currently, people characterize all ecosystem chains as clustered. For example, you have Optimism superchain. You also have like Polygon's ag layer. Aside from the intent-based protocol where a user just sends a request over network and has no guarantee of what comes back, you also have these inter-cluster communication and intra-cluster communication. So for intra-cluster, for example, within the Optimism superchain ecosystem or app layer, you have protocol-defined sequencing and deterministic cross-chain ordering rules, but it could be a little bit centralized. For inter-cluster, however, we have to coordinate these communications. So the consideration for that is settlement dependency. If Polygon settles while Optimism reverts with some fraud proof after Saturday, what do the Polygon do? So like user might have burnt some coin from Polygon and try to mint something on OP, where OP actually revert. Then the user is stuck somewhere, right? The funds are missing. So that's settlement dependency. and messaging facilitation. So who's actually sending the message from Polygon to OP, and how do both chains read and write these messages and process them, right? So these are the consideration. Are we gonna do like a shared sequencing protocol? Like Espresso, right? People know about Espresso from what they're trying to do shared sequencer for all layer 2s, but how much are layer 2s willing to give up their sequencing right? Because it's a very, is a very juicy business, I guess. Right. If we don't have shared sequencer, should we use like a coordination protocol? In the coordination protocol, on the other hand, some third party will run the coordinator to relay, to facilitate the message relay. But the rollup do have to opt in, and there's also certain amount of trust assumption. An example of that is also proposed by Espresso, is called CIRC, Coordinated Inter-Rollup Communication. So if Espresso cannot get people to actually use their sequencer, they kind of like opt out, like kind of back out into a second tier solution where they run a coordinator to like coordinate these message passing. So that's the intuition for this. And this brings us to Gwyneth, which is what we try to build to improve this space, right? So for Gwyneth, so inside Gwyneth cluster, we want to build a atomic synchronous cross-chain calls. We want to facilitate an atomic synchronous cross-chain call that are based on the base builder themselves. And then as a bonus point, we also want to allow L1 composability conditioned on the lock of L1 states. So depending on the status of pre-confirmation, if we have somewhat weak pre-confirmation, we can do L1 reads. If we have a very strong pre-confirmation, we can do L1 writes as well. And what do I mean by base builder? Is literally a builder over there that are literally building for both L1 and L2. So in this case, this builder connects to both L2's RPC and also L1. Right, so like inside the DB, it has like transaction from all different endpoints. And what it's building is packaging up, like L2 blocks and directly forming a proposal transaction and insert that into the L1 block. So the builder has full control over what's happening in the L1 block. You can imagine if we go to Titan, if Taiko goes to Titan and be like, oh, please like sequence our block as well, and Titan will just do it for us. And it's also very easy for them to just insert that Taiko proposal transaction into the L1 block that they've built. And also like they will propose the block through the regular PBS pipeline, and this block will finally be ended up on L1. So that's intuition. For out of clusters, for inter-cluster communication, we want to enable atomic synchronous cross-chain call through some coordinated message relay. Again, I will use CIRC as an example of the framework proposed by Espresso to like demonstrate how we can be compatible with out of cluster communication. In order to do that, we also have a generalized multi-proof framework where we leverage the power of real-time proof, which is in our case TEE, to ensure the consistency of inbound and outbound messages. Right. To start of like how we do atomic synchronous cross-chain call within the Gwyneth cluster, I'm going to go over booster rollup. So this is a demonstration of how booster rollup works. So booster rollup is basically like an execution implementation of cross-chain execution environment. So in that example, we have Gwyneth chain A and chain B, like the pink one, the pink chain and the blue chain. And the base builder will stay for both chain for their transaction and states, right? The builder or the L2 proposer with PBS will purchase rights to sequence for both chains. Like in our case, I think in our protocol design, we might sell execution ticket, but you can also have some sort of I don't know, look ahead or smart contract or like gateway-ted smart contract for like who's going to sequence your chain. But anyways, but both builder has to have sequencing right to propose the block, and then this allows them to gain an exclusive state lock for the initial states of chain A and chain B, so they can start building, right? So by locking, after locking to the initial state, we have this S0 sub A and S0 sub B, and they can start processing cross-chain transaction. Let's say there's like one transaction from A that tries to like call chain B in A span pool. Like this will be like an example of one of the calls, right? We're trying to transfer money from A to B. So in our booster implementation, you subtract the balance from chain A. So this transaction will be running on chain A's context, and it will like subtract balance from message.sender, and then we'll call this X call option pre-compiles, which is like a custom modification that we do on the ZK on the VM, on the EVM, right? After calling into the sorry, I was like stuck with like ZK idea, but okay, EVM pre-compiles. The nodes will automatically go through this context switch that we swap out the database from chain A to chain B. So by the time that we're calling into this mint function, we're already executing in chain B's EVM environment. Yeah, so this is like how we go context switch. And this pre-compiles in Gwyneth REVM implements the booster role. It's a implementation of the booster rollout, which lets you to context switch between L1 and L2 DBs. And at the end of execution, of course, we're gonna apply the state diff back to A and B accordingly. So we end up with S1A and S1B, and then by this proposed block operation, we propose block back to A and B with an execution ticket. You kind of like apply the state diff back. Like my mental model of thinking about this is kind of like when you write code, you check out a branch, and then you write some code, and then you make a PR, and that's like literally the diff back to the main branch, which is the chain itself. And if you like in a Git working workflow, like a branch is literally a fork, right? If you fail to like merge it back to the main branch, you ended up with a fork, right? Yes?
Can you have a merge conflict in the system?
No, because there's state lock, right? That's why I emphasize on the fact that you have to buy execution ticket. If a protocol sells you the execution ticket and also sells some other people the same execution ticket for the next block, that you have a conflict, that is basically equivocating. Yeah. And what are the specific considerations for these execution implementation? Right, we have like two potential things that we can do. Since we use the base builder itself as the facilitator of message passing across chain, we kind of transition message passing into context switch. So in a message passing protocol, transaction on A calls B needs to encode some call as call data and then use a relay or coordinator to pass it over and await the return. That's a very like asynchronous setting, right? Whereas in a context switch building process on the same builder, transaction on A calls into B and modifies state directly. And we record these state diffs and pass it back and pass back the return. And A will like continue with this call data and return pair from B. So like in this case, like obviously like the same transaction comes in, and the triangle is like the state diffs that are generated by executing this non-native call for B on the same builder. And then when this transaction ends, like the literally return data will be popped back from the stack back to A, so A can continue with the expected result that he gets from B's execution context. So when a individual nodes are syncing, they will see like normal transactions and state diffs that are generated by non-native call. Like someone calls me, so it generates like a bunch of diffs on my status. And then call data and returns, that's like when I am calling someone else and try to expect some return from someone else. So these are when an individual node from B is syncing, this is basically what it will see. And then like you would just like directly apply either the state diff or directly use the call data and return pairs from some other chains. Okay, so what are the comparisons between the two models? Like I said, message passing is asynchronous in nature. There's no state lock assumption in the model itself because it's not in the same building process. So we need to use proof to revoke calls that fails to ensure atomicity as settlement. So basically what I mean by that is if the return message passing failed, then basically the call data, like so whatever, the previous transactions should all be reverted at once. So that's atomicity. And then you have to enforce that later on because you cannot enforce that during the message passing process. However, context switch is synchronous with state lock because you're literally running the whole thing in the same builder. So a syncing node who will just like simply apply the state diff. But the downside is that we might lose some property for DA because if we just directly apply the state diff, the call data that are the execution trace that incur these state diff will be lost. So if a syncing node see a triangle, it actually doesn't know what initiated, what causes the triangle, right? Yeah, so that's the comparison of these two models. Right. And now it brings us to like L1 composability. If we have a super builder, like I said from previous slide, that builds for both L1 and L2, then we can basically compose L1 freely. So because like the super builder can interleave the L1 and L2 build, you can have a bunch of L2 transactions and then L1 and then back to L2, right? And then you use the same model that we use for the state diff stuff. So like the super builder can basically do anything. But that is actually quite hard because like in order to do that with vanilla PBS, the builder will have to obtain sequencing rights for both A and B, and somehow also win the PBS auction to build the L1 block. So let's say you're an operator running the two rollups, you have to have a builder that wins almost every L1 block. And that is like super unpractical for a rollup operator. But what do we have though, like to enable this to happen? We have pre-confirmations, right? The lowest, the most minimum offer of pre-confirmation is inclusion pre-confirmation. That literally means the builder can go to some L1 validator and say like, please include my transaction on the next block, and the L1 validator will give that promise with some economic backing of some state, right? In that case, we can ensure that both A and B, which is our cross-chain building Gwyneth layer 2s, can settle it on L1 somewhere during the next L1 block. However, in this case, the builder cannot assume anything about the L1 states. The L1 states are not locked. So you can't read from L2, neither you can write, right? Because like the L1 state is changing, per transaction for the whatever transaction that the builder might include before you. So you basically can't assume, like for example, like token price of Interswap is whatever, like you don't know. So this enables the interleaving building of layer 2s because we're still within the Gwyneth cluster, but we don't have L1 composability if we only have inclusion pre-confirmation. But what about better pre-confirmation? If L2 builder gets pre-confirmation of the current L1 validator that I'm going to include your transaction at the very top of block, then it can basically read L1 state directly from the last block and emits write at proposal times. So if I know that there's no one comes ahead of me, I can basically take the previous L1 block and read from that state and make sure that these states are fresh, right? And then after I do some state modification, when I propose, I'd be like, okay, I actually want to update L1 price, the token price of some Uniswap contract because I did some trading on L2s. Yeah, so in this case, we can both read and write, but we can only do them once because like you don't have a exclusive view of the entire L1 block, so you can only do it once. Whereas if we have execution pre-confirmation, in that case, like the builder will monopolize the whole L1 block by pre-confirming the execution of the whole block space. So that's the case where the builder buys off the entire L1 block, but through a execution pre-confirmation. Yeah, so in that case, you can interleave L1 and L2 block building as you want. Okay, so what about intercluster composability? Now we've talked about everything that Gwyneth can offer on its own. We also try to generalize our framework to communicate with the other builder. And in that case, this will have to be a message passing protocol, right? Assuming we're communicating with a non-based cluster where Gwyneth don't have the state lock or any assumption of their settlement. So I don't know when and how this chain will settle. So the message has to be relayed by some third party. Well, another caveat is we assume in real-time proof of the other chain. So optimistic rollup is not allowed because there's a 7-day fraud proof period, and we think that that's a big security risk. Yeah, and in this case, so I will show an example with Espresso's CERC, the coordinated inter-rollup communication protocol. In that protocol, they assume an Espresso coordinator that's going to do all these message relay, and they also define an inbox and outbox smart contract for each chain that that the message can get sent over. Specifically, if someone from Gwyneth tries to call this Espresso chain and burn some token and try to bridge the token to Espresso and mint the token over on the other side, the cause itself will go to an outbox, right? And the coordinator will basically either relay or re-execute the transaction for the other chain. So the call data somehow ended up in the inbox. And this is a very a built-time, real-time process at which this coordinator will probably listen to the mempool of Gwyneth and also the mempool of Espresso. The relays they just grab the message from here and relay to there, right? And then after Espresso's execution, the return data gets relayed back. So what are the security critical elements here? So first of all, message validation, right? We actually don't know whether these relayed messages are true. So one solution is we can have it with zero knowledge proof, or we can do it with pre-confirmation. And also settlement validation. We will have a generalized proof framework that recursively proves the validity proofs of all chain. So after Gwyneth settles sometime or Espresso settles sometimes, there will be a settlement validation, generalized proof to validate the execution of the entire chunk. And also cross-chain clearance. So there might be a case where the execution integrity is guaranteed, but the accounting is wrong. Let's say Gwyneth burns 10 tokens, but Espresso only mints 9 tokens. So both mint and burn correctly, but the accounting between those are actually wrong. That's also a very likely scenario where we have to deal with. I actually don't have much time, so I'm just gonna go over it very quickly. So what we come up with is this glue proof that glue everything together. So in this cross-chain relay situation, if Espresso and Gwyneth settles in one block, so the settlement will also imply the verification of their own proof, right? So when they settle, the execution integrity is guaranteed. But as they settle, these two protocols are also supposed to fill out a in and out like balance sheet on L1. And L1 will check that balance sheet, right? But we actually don't know at this point whether the balance are correct, right? Whether the balance sheet checks out. We have to wait till the next block to see whether money in actually equals to money out, right? So what you do is you run a TE proof over the entire previous block, and if anything goes wrong, and you realize like assert in doesn't equal out, you kind of find out what are the exact transactions that cause this inconsistency, and then you like cross them over. Towards the end, like you like reapply the new state root because you crossed out certain transactions from both espresso and Gwyneth. So the proposed state root are S0. You actually ended up with like S prime after a rebase of your balance, right? Of your state root. Yeah. So in that case, like for the fact that we also like cross out this whole batch, we also ensure atomicity, and we ensure that no one can be malicious to the state of the chain. That's also why I'm saying like TE is very important, because we need like real-time settlement for both of these, and we also need real-time proof to prove the entire L1 block that whether they themselves are verified and whether the accounting is right. Okay, so what we're trying to do here is basically gluing the finalities, right? We're gluing together the settlement of a Gwyneth cluster and an espresso cluster. We also allow cross-block settlement because as long as your final generalized glue proof are run on TE, you can prove over multiple L1 block where every different chains has different settlement schedule, right? You can glue over like 3 previous blocks such that all of the message relay that happens in this 3 previous L1 block time are atomic. And you also, and also there's like one more question. Should each message be proven, right? And we actually realized that with the glue proof, you don't need any proofs per message, right? Because if anything, if things can be atomically executed and atomically revoked, you basically, all these things can be optimistic. You can optimistically relay the message without each chain checking like the other chain's consistency. And then if later on in the glue proof anything goes wrong, you revoke them all together. So you don't even need a ZK proof per message. So this is like very efficient for the neutral relayer as well. And what about pre-confirmation? So does pre-confirmation give us better property for the L2 that are cross-communicating? I would say yes, because when relaying message from A to B, the relayer get a receipt from B and send it back to A. We actually realized that you can build a synchronous system with execution pre-confirmation even without the glue proof. Because for every step that, for example, Gwyneth are calling Espresso and having an execution pre-confirmation of Espresso's execution, then the build time process itself will check out the consistency of the error leaving, token transfer or whatever. So but like the whole security assumption will be only based on economic security. Yeah, and this concludes my talk. I think I don't have much time, so thank you very much. Okay, one question.
Why can't you use optimistic proofs?
Because it will revert, right? Like I said, like if there's like cross-block settlement and then the cross-block settlement lasts for 7 days, then
wouldn't the transaction ordering is guaranteed with optimistic role? Like I know the order of the transactions. I don't know the execution of it. That's after 7 days. That's finalized. But I do know the order.
But because they don't have instant finality, right?
Well,
you know the ordering, but like by definition, they still might revert, right? Because like there's 7 days of revert period, like.
Well, the state can revert, but the transactions themselves are finalized.
You actually need the state to be finalized, right? Because like I mint 9 token and the other person like burn 8 token. Like I want the after fact that these tokens are burned.
But I guess like if the transaction itself.
Right. So like there will be like a case where the transaction itself that tried to burn 8 tokens are still there, right? But then it might fail because there might not be enough tokens to be burned. So like I will be like minting 8 tokens anyway, not knowing that if the other transaction on the other chain will be success or not.
Okay.
So you need the after fact that it is.
So you need the state.
Yeah, you need the execution pre-confirmation.
Okay.
Yes.
Okay.
Right. I have to go. Thank you very much.
Thank you.